So speaking of Xilinx, our next presenter is José Alvarez, talking about challenges and opportunities in accelerating OpenCV. José's been involved in architecting, designing, and implementing image processing and video products for a variety of industries and companies over the past 20 years. He's actively participated in major industry inflection points, most notably in the development of MPEG-2 HDTV, desktop computer graphics, time-shifting DVR technology, MPEG-4 AVC, and extensible processing FPGA platforms. Jose earned bachelor's and master's degrees in electrical engineering from the City University of New York. His work's been granted 28 US and European patents, with several more pending. He's currently engineering director for video technology at Xilinx, where he's responsible for R&D, video and image processing IP cores. And for any of you who have already visited the Embedded Vision Academy section of the Alliance website, you've already seen a lot of his very informative video tutorial material that's there. So thank you, Jose.
Thank you. Thank you, Brian. And welcome, everybody. Can you hear me? Yes. Great. So thank you very much. I'm going to be springing forward from Mario's talk. Mario concentrated very well on telling you what the tough problems are in implementing embedded vision systems in hardware. Right now, I'm going to tell you a little bit about more of a software-oriented approach to those embedded vision processors. This is a company introduction. Xilinx, we're one of the founding members of the Embedded Vision Alliance, so I won't concentrate too much on this. So the scope and motivation of my talk is, of course, embedded vision is pervasive, it's everywhere. Vision processing algorithms are maturing, and now with our present technology, they're very feasible in embedded systems. However, implementing very practical embedded vision systems in hardware, in real systems, it's very difficult. And so you have to really pay attention very carefully to your architectural partitioning, especially since it's never all software, all hardware implementation when you want to implement embedded systems that are very, very efficient. And so what winds up happening typically is that you need to accelerate computationally demanding functions, just as Mario indicated. And you want to have a software base where you can spring forward from that. So using open source, it's a good start, Linux, et cetera, and all libraries. And this is where OpenCV comes in. As Gary Brasky pointed out earlier, OpenCV is open source, is freely available, and a great platform for developing embedded vision and computer vision applications. So it's very practical, it's very efficient, it's a very extensible choice. However, implementing in processors only limits the capacity of what you want to do. And so you have to, a good way to start implementing accelerators for OpenCV is to consider high-level synthesis. So OpenCV, as you will see later on, lends itself very well to acceleration using high-level synthesis. So I won't deal with OpenCV. You've seen from Gary all that it is. So I'm going to start by just talking about productizing OpenCV for embedded vision. So obviously, your real-time requirements are a big factor in what you do. High definition, ultra-high definition video streaming, it's a very important consideration. Many times you have multiple streams, not just one sensor, but multiple sensors that change. So you have to consider size, portability restrictions, and most importantly, memory requirements. You've seen the examples from the previous talk where very quickly you get into very high memory requirements. So your memory storage and handling paradigm has a lot to do with how efficiently you implement your systems. One of the challenges of implementing your systems from OpenCV into hardware is dynamic memory allocation. OpenCV uses dynamic memory allocation freely, and so when you consider embedded systems, it's really a big factor, as well as latency. Low power requirements are many times directly related to how much memory transfers you have. So obviously having a system that is fully integrated into one single platform becomes a big advantage, as well as having the caching mechanisms internally to reduce that memory bandwidth. Another big challenge for OpenCV implementations from the software environment to hardware is floating point processing. And so you need to consider processors that have really right support for floating processes. And finally, verification and validation. All of those of you who have been involved in creating reliable hardware systems know very well that verifying and validating your implementation, bit accuracy and timing accuracy is really critical. So I'm going to talk about first about very generically a very high level design process. So typically we start designing our algorithms in modeling. And modeling typically is done in C, C++, or any language that is easily accessible in your large computing platforms. You zone in your algorithms, you determine what is right, and then you decide, well, okay, now let's look at system partitioning. It's based on profiling, it's based on metrics out of your source code, and then you start to do architectural partitioning. What parts of your algorithm are going to go into software, and what parts into hardware? And then the implementation step is iterative step where you do testing prior to release. So in architectural partitioning, you have to pay attention of what parts of your algorithms are controlled. Lots of control, lots of intelligent processing. So in smarter vision systems, your intelligent part of your algorithm, the one that it's very flexible, it's really typically run on a CPU. And every parallelizing processing, like SIMD, is run on hardware. So memory transfers, as I mentioned before, are very, very key. DMA transfers, you saw from Mario's talk, are critical in implementing your right system, as well as interface requirements. And you have to make a decision very early in your design. If you're going to use hardware accelerators, what mechanism are you going to interface hardware accelerator with the rest of the system, as well as libraries that are already available to support your hardware implementation as well. And a simple example, for instance, is high-quality image scaling, one of those algorithms that are better done in hardware. So some of the challenges of really accelerating OpenCV, it's really high throughput and constantly changing requirements. Also, portability across platforms. If you're going to design a system that is targeted to a specific platform, you have to really think about, well, would you be able to reuse that system? So reusability of your algorithms is really a critical decision. But you can implement embedded systems based on OpenCV and on multiprocessors, GPUs, ASSPs, and as well FPGAs. So today I'm going to concentrate on the architecture that Mario indicated at the end of his talk, which is called Xilinx, which is a system-on-a-chip processor that integrates very efficient dual-core ARM Cortex-9 processors with Neon extensions and very rich FPGA fabric around it. But most importantly, I want to talk about the development methodology, because the development methodology ultimately winds up affecting your time to market and your time to integration for your system. And obviously, we want to preserve the original intent of OpenCV, which is experimentation, very quick what-if scenarios. So let's look at the development process from this perspective. At the very bottom, you have the same diagram that Mario presented of Xilinx processors, where the yellow portion is FPGA fabric, tied in very tightly integrated with the processing system in the upper left-hand corner with very high-speed connections, thousands and thousands of connections, which bring in the whole system together into one single SoC. The processing system in the upper left-hand corner contains all of your interfaces, Ethernet, USB, etc. And so all of that, it's supported through Linux and other operating systems. Now, based on this, you start your design from your requirements, and then you have a software specification path, a hardware specification path, and that could be tied together with high-level synthesis tools. So you go from your software specifications to your accelerator environment. So you have to first change your architectures to start to think about in terms of accelerators for those functions that you have determined that need accelerating within OpenCV. So let's go over that. So The opportunities and challenges of using high-level synthesis are many. One advantage is definitely that you start developing your algorithms in C and C++, and you can continue that into hardware RTL accelerators using your original software infrastructure. With analyzing the performance of your system, you can determine which parts of that C code need to be translated into RTL, into hardware, and therefore you can use their hardware accelerator architecture. Not only that, but your verification function, it's already included in your C test benches, so there's no need to create any RTL test benches. For those of you who have created hardware, you know very well that it's a big work to create test benches to match your C model to your actually hardware architecture. So that allows you to fast prototyping and the partitioning of your architecture in a very convenient way. And eventually, essentially, high-level synthesis hides the physical synthesis place and route that typically goes together with hardware implementations. So from a very top-level perspective, high-level synthesis really is about abstraction. So you have your algorithmic description, your data types, and your interfaces that are abstracted. Then you use synthesis directives together into the tool to control loop and function pipelining, to automatically extract task-level parallelism, matching delays, schedulings, resource allocation. All of that is done automatically for you by the tool. High-level synthesis, Vivado high-level synthesis does all of that for you and also generates automatic interfaces. Now, these interfaces are very, very important because in Xilinx's case, we standardize on AXI interfaces. So all of your interfaces between your software mechanism, your CPUs, your dual-core ARM processors, and the hardware accelerators are AXI-based, very high utilization interfaces. So eventually, you get an RTL IP implementation, backward compatibility to C and C++, and the automatic RTL generation. So one example of a typical system that is very amenable to this type of implementation where you have your part of your code in software and part of your code in hardware is driver assistance, where you take pictures of the road, you perform lane detection, some tracking, and some decision making. So essentially, this can be implemented in OpenCV by using the RGB to gray conversion so that you work only on luminance pictures. Then perform some histogram equalization to enhance the details and features of your picture, some edge detection using Canny or Sobel operators, etc. And then finally, a Hoff transform to do feature extraction. So this is performed on very high pixel data rate images, perhaps even multiple sensors in one system. And this is the part of the algorithm that requires hardware. It can be implemented in hardware. And this is the part of the algorithm that can be performed in software. So again, your top-level partitioning is very critical in your implementation, but eventually it always comes out to a mix of hardware and software. So what does that look like when you use OpenCV and the programmable SoC? On the left-hand side, you have your OpenCV application. I've indicated at the top and at the bottom image read operations. So these are very conveniently provided by OpenCV, where you can read using libraries already existing. And in the center, the OpenCV functions. You can reuse the portion of your code that runs on OpenCV on the ARM processors verbatim, and then that runs in the processing system. Then, once you have determined what parts of your algorithm need accelerator, you use high-level synthesis based on your C code. And I'm going to give you some examples a little later on so that you get the flavor of what that C code looked like, C++. And you start to wrap that so that it's a synthesizable block that is run, as it says here, on the programmable fabric. Now, how do you tie them together? Well, we provide with functions that convert from the OpenCV infrastructure to the AXI interconnect that I mentioned earlier. So both at the beginning, at the input, and as well as the output, you have automatic conversion routines that tie your accelerators from your FPGA fabric directly into the processing system. And that is all run in FPGA fabric. As indicated there, those are the very high-speed connections in blue from your processing system in the upper left-hand corner to the FPGA fabric. So that would be the type of design methodology that you would use when you want to use OpenCV, whatever is existing already today that runs in the ARM cores, and then accelerate one function at a time in your application. So I'm just going to give you a very, very, very simple example of the type of functions that are provided. Mostly are data type functions. We essentially concentrate on video functions that are in the image processing category of OpenCV. Obviously, as Gary pointed out earlier in the morning, there are many, many categories, but we've started to concentrate on the image processing part of it because this is what we feel that it's the first level acceleration that you need in your system. The idea here is really to provide you a way to use high-level synthesis to eventually implement your design in a very efficient manner. So, very quick example. Let's say that you have an OpenCV function that is fairly simple. It's an erosion function at the very top. So at the bottom, I've shown you the implementation in high-level synthesis. Now, there's a lot more lines, no question about it, but all of them are pragmats that essentially set up your input and outputs in green. So you have to specify, well, my input is an AXI stream. My output is also an AXI stream. And you have to tell it how many rows and columns your image has. Once you have done that, it's basically something that you use for every function to determine the interfaces. And then the ports are directly as rows and columns. And then finally, you allocate images, two RGB images in this case, and then in purple, the eroding function itself. So there's some, and obviously the conversion from AXI to video to matte. I don't know if you could see this from way back there, but these are exactly the code that is represented in the picture that I showed you a couple of frames ago. So another example is you define at the beginning of your program the high-level synthesis video libraries is at the very top provided. Then there's always a main as well. You use standard OpenCV file formats and type for loading the image, create the image, and this allows you to do your development initially perhaps in the software domain. Perhaps you're working on your Intel-based platform. You transfer that into the ARM system. You can run everything completely in hardware, but decide what you're going to accelerate. So once you decide what to accelerate, you convert that stream into something that can be communicated to the programmable logic portion of the SoC, and then you perform your synthesizable function, image filter. And I'm going to show you in the next slide what image filter looks like. And then finally, once image filter returns, you convert that data that it's communicated through the AXI interfaces, both source interface and destination interface, into, again, back into the image plane, and then finally you save the image. So now, what does that image filter function look like? Well, essentially, again, you start by defining your high-level synthesis video in AXI structural libraries. And again, you convert into a format that it's readable by your accelerators in FPGA fabric. And then you perform your functions, which can be a combination of functions that are, in this case, all high-level synthesis ready. And then the final conversion for storage into your system. So in conclusion, OpenCV is an excellent choice for implemented embedded vision systems. It's very clear. The question is what your embedded vision system is and what your target performance is. For very high data rates, essentially you can use OpenCV in a standard x86 platform because it allows you to a large range of computer vision functions. But once you want to really optimize for an embedded system, a smart vision system that is optimal, then you have to really pay attention to your architectural partitioning. And hardware acceleration within the context of an SoC that is fully integrated with very powerful processors and FPGA logic, it's very optimal for converting a combination of OpenCV functions to run in software and as well in your accelerators. Because high-level synthesis is based on C and C++, which is really the language where most functions in OpenCV are done, you have a very clear path to reuse your code that you've been developing. Not only that, but simulate the code both purely in the software domain in a combination of the two. Even while you're developing, you can choose which functions are accelerated and are translated into the FPGA fabric by using the communication mechanisms that I've shown you before. But as any other tool, high-level synthesis is something that you need to learn. There's very specific applications where it's very, very, very efficient. For image processing applications, two-dimensional processing, data transfers, it produces very high-quality RTL. In many cases, what we found, it's just as good as what we could do manually, but much, much faster, and it allows you the opportunity to experiment. And you know very well, those of you that make embedded vision systems, that it's not always straightforward, that experimentation. And so finally, you have to think about your optimal development environment and your time to integrating the system and to market. And so high-level synthesis is really a very good match for our applications today. I've given this, you'll get this or in your USB drive. So these are areas to explore further. At the very bottom, we have an application note, 1167, which shows you in much, much more detail what I've shown you today as to how would you use a specific board and how would you implement OpenCV functions or even generic high-level synthesis functions. Okay, any questions? What's that? So it's pricing on devices. Well, these devices range in prices from tens of dollars to hundreds of dollars, depends on the amount of FPGA logic that you have in your device. And the processing system, the dual-core ARM Cortex-9 processors, including all the interfaces, USB, DDR, Ethernet, it's all included in all of the devices. The price differential is how much FPGA fabric you have, which again is completely based on your application. Maybe your application can be run mostly in software and only very key functions are accelerated. So it's, that's really where you start.
For a mid-level device, what would be the power consumption running HD video processing?
Right, so for a mid-level device, what would be the power consumption? That's a good question, and we're in the process of characterizing that. It depends on your data rates. It depends on your memory bandwidth that you use externally. So unfortunately, it's not an easy question, but it's definitely in line with similar processors, similar dual-core ARMs with the amount of fabric around it. It's certainly in our latest 28 nanometer technology, which is very power efficient.
So 2 watts type of thing for kind of a nominal ballpark?
I don't have the right numbers, but I can get them to you, the specific numbers one. Yeah.
There's this question over here. Maybe I can answer that. It's not so much of a power issue, but of an energy issue. If you have less power, but you need more instructions to compute, obviously consume more energy. And this technology can allow you to consume less energy by having less computations.
Right, so that's an excellent point, and it goes to your architectural partitioning, where you can do massive parallelism and then just reduce essentially your instruction capability. Also, another good point, and thank you for reminding me, is the fact that if you have an integrated device, you can essentially use the same techniques, having an external CPU tied into to an FPGA. There's nothing that says in OpenCV that you cannot do that, but obviously having two separate devices, it's actually far more power consumption hungry than an integrated device. Mark.
Jose, this looks like a great infrastructure of just moving OpenCV algorithms from the ARMs to the programmable logic. I was wondering, what is the long-term plan from Xilinx for implementing OpenCV functions? Is this something that Xilinx is going to tackle, or is there opportunity for IP providers to maybe provide that the next step?
Right, so that's a great question. So what we've started to do is concentrate on the basic functions, what we call math.age, provide you with the fundamental math functions. As I showed you very briefly in one slide, multiple data types, conversion routines, and started with the image processing set of routines from OpenCV. The ideal would be if within this infrastructure people start to contribute routines to this infrastructure. We are continuing to more and more convert OpenCV functions that are critical for processing systems.
Hi. Typically, when developing these algorithms, when you're prototyping in C, you have to be very careful about, for example, what kind of data types you choose and what kind of algorithms map very well to the FPGA logic. Now, you talked about this high-level synthesis tool. Do we still have to be as careful, or does that tool take care of a lot of these things that you have to understand the FPGA to develop these algorithms?
Yeah, great question. So I'll tell you, one of the things that you do, as you probably know, when you implement these systems in hardware, in RTL, is that you decide, let's say, on a 12-bit data path, and then you have to keep all your extension of the data path as you go, addition, subtractions, multiplications, etc. And then you keep on growing that data path, and you make decisions if you're working on an integer data path as you walk across. With high-level synthesis, you define that at the very top, what your width is, and the tool itself takes care of it as you move along. So that in itself is quite a savings in time, where you can experiment, by the way. You can tell the tool, of course I didn't go into all the details, but you can tell the tool whether you want to optimize for area or power or all of these things, and it gives you multiple systems where you can decide whether you're meeting timing, you're meeting performance, etc., all very integrated through the Vivado set of tools that we provide.
A follow-up on that is typically when we have to resynthesize a core, it's not like compiling on a C compiler where it takes about 3 seconds. It could run 10 minutes to 2 hours to maybe a day or so. Mm-hmm. If we change one variable, has Xilinx addressed something?
Well, yeah, definitely. With with new Vivado set of tools, we have vast improvements on synthesis and place and route. But the thing with high-level synthesis is that you don't even have to go there. You can run your actual hardware, which is bit accurate, clock accurate in the C domain. So you don't have to go into the RTL domain, which is a great advantage. So ahead of time, and you probably are also wondering, what about debugging tools? What about all this stuff? And surely there are debugging tools, but what you really want is not really debug at the RTL level, right? You want to debug at the higher level, at the C level. And that's one of the advantages that OpenCV with HLS really provides you. Right, good question, thank you. Okay. Another question?
Well, in OpenCV, we use a lot of a smart pointer. So does when we do the high-level synthesis, does it take care of the memory allocation and delocation?
Yeah.
How does it handle?
Yeah. So as I mentioned earlier in my talk, dynamic memory allocation is really one of the challenges, right? Because OpenCV wants to do memory allocation. So what we do is we implement functions that use a streaming mechanism, and so that there is no memory allocation. So you have to work in the context that the accelerators that operate in hardware, read from a frame buffer and write to a frame buffer, and that's your main ways of communication when you're using memory-to-memory transfers, or when we call streaming, then you can connect accelerators together. But again, it's not a dynamic memory allocation, so you cannot use dynamic memory allocation, right? Yeah. So that's one of the design things in mind that you have to keep when you translate OpenCV functions directly to high-level synthesis. Yeah.
Any other questions? Thank you very much for your questions.
Well, thank you very much.